Welcome to Sensors and Industrial Instrumentation, Chapter 2. And the index for this is measurement of various non electrical quantities which are not electrical. The first one is measurement of vibrations. The second one, measurement of acceleration. Third one is you learn a detailed learning on these concepts, and finally we'll have some model problems on these concepts. When you look at this word vibrations, it's not an electrical quantity, so we'll measure various non-electrical quantities. One from that is vibrations. Acceleration, as you know, is not an electrical quantity again, so both these come under non-electrical quantities. Now let's look at some mechanical devices as primary detectors. Now measurement of non-electrical quantity. Let's take some force that is applied to this elastic element, and due to which there will be some displacement, and this displacement is given as the input to the transducer. As you know, transducer converts one form of energy, anything, to the electrical output. So the output of this would be an electrical quantity or electrical output. So you'll apply some force to this elastic element, by which you'll have some displacement on it, and this displacement is given as input to the transducer, wherein you'll get the electrical output from this transducers. So this is called as a secondary transducer. Now let's look at some type of mechanical devices as primary detectors and their operation. Now the different types are contacting spindle, pin or finger. The second one is elastic member. Third, masses. Fourth, thermal. Fifth, hydropneumatic. Now let's see one by one. If you look at this type, contacting spindle or pin or finger type, it converts displacement to the operation is displacement to displacement. Now when you look at this elastic member, there are five types in this. One is proving ring, which converts force to displacement, and Bourdon tube, it's pressure to displacement. Bellows, you can see it's pressure to displacement. Diaphragm, it's pressure to displacement. Spring, it's force to displacements. In this you can see there are two devices which convert force to displacement. That means their input are forces and the output are displacements. One is proving ring and spring. And if you look at the rest of them, Bourdon, bellows, diaphragm, these three convert pressure to displacement. All these three convert pressures to displacements. Now let's look at the third one. Let's look at the masses, the third type, wherein you have seismic mass, pendulum scale, and manometer. The seismic mass will have operation as force to displacement, as you have seen in the spring and the proving ring in the last classification. And the pendulum scale converts force to displacement, and manometer converts the pressure to displacement. So this manometer is a pressure to displacement conversion device. Seismic and pendulum are force to displacement conversion devices, and all these three come under mass type as mass. Now coming to thermal type detectors. There are three types in this: thermocouple, bimetallic strip, and temp stick. A thermocouple converts temperature to electrical current, and bimetallic strip will convert temperature to displacement, and temperature stick will convert temperature to phase. So these are the three types in thermal type primary detectors. Next, coming to the last type, hydropneumatic. So in hydropneumatic, you have static, dynamic. In static, you have float type and hydrometer type. This float type, hydrometer type, you have fluid level to displacement or specific gravity to displacement. So float will convert fluid level to displacement, and hydrometer has the operation of specific gravity to displacement. Now coming to this dynamic type of hydropneumatic primary detectors, the first one is orifice, venture, tube, and vanes and turbines. Now, if you look at this orifice, it converts velocity to pressure, and venture, it also converts velocity to pressure. Pitot tube is also velocity to pressure. Now vanes will have the operation of conversion from velocity to force, and turbines will have linear to angular velocity conversions. So these are the mechanical devices as primary detectors. This is the type and this is the operation. Now, whatever we have seen are these types: contacting spindle, pin or finger, elastic member, mass, thermal, hydropneumatic, and their operation. We have seen all these things, all these operations we have seen. No, measurement of vibrations. As you know, vibrations is not an electrical quantity, and we are studying about the measurement of non-electrical quantities. So, measurement of vibrations arise because of growth of environmental testings. So, what is the need of this vibrations measurement? Is it's because of the growth of environmental testings. So, instrument can withstand levels of vibrations. So these measurements are generally carried on rotating and reciprocating machinery for analysis, design, troubleshooting, and other purposes. So these measurements are very important. If you have some vibrations which are more severe, then the rotating machines may get damage, or during design you have to take utmost care to reduce these vibrations or to minimize the vibrations. That is how it becomes very necessary to measure the vibrations. So it's also like carried out in station turbines and generators. As you know, turbines are mechanical devices which are rotating, and generators are also rotating devices. When these devices which are rotating are subjected to large vibrations, then there will be damage to the machinery, or the machinery may break out. So in order to avoid such things, measurement of vibrations is very important. Now, what are the different natures of the vibration? Most vibrations are sinusoidal displacement of the vibrating member about its mean position. So they are, most of the vibrations are sinusoidal displacements of the vibration member about its mean position. The quantities involved in measurement of vibrations are: the first one, displacement, velocity, acceleration. So what are the quantities involved? Displacement, velocity, acceleration are the three quantities involved in measurement of vibrations. So what are the different natures of vibrations? Most of the vibrations are sinusoidal displacements of the vibrating member about its mean position. And the quantities involved in measurement are displacement, velocity, and acceleration. No, nature of vibrations you can represent mathematically as the mathematical notations as x. If you differentiate, it is v, and if you still differentiate, you'll get a. That means x is displacement, you get dx by dt is velocity, and acceleration is rate of change of velocity. So x is displacement. If you differentiate, you'll get velocity. If you differentiate velocity, you'll get acceleration. This is also equal to dx square by dt square. So that's what is written here. X, if you differentiate, it is v, that is nothing but dx by dt. And if you differentiate v, or rate of change of velocity is nothing but acceleration. I have also written as d square x by dt square. Now, for sinusoidal vibrations, displacement is given by x of t is equal to x naught sine omega t, which is the representation of a sinusoidal vibration signal or sinusoidal signal, where x naught denotes its peak amplitude or magnitude, and omega represents the angular frequency measured in radians per second. I repeat, for a sinusoidal vibration, displacement is given by x of t is equal to x naught sine omega t, where x naught is the amplitude or magnitude or peak amplitude, and omega is called as the angular frequency, whose units are radians per second. No, V of t is equal to what V is equal to. I told you what is V is equal to. It is dx by dt. If V is a function of time, so d by dt of x is also a function of time. So you'll write d by dt of x of t. V of t is equal to, and this can be written as differentiation of. So we can write what is x of t. If x of t is equal to x naught sine omega t, what is dx of t by dt is equal to x naught is a constant sine omega t, it is omega cos omega t. So that's what it is written, x naught omega cos omega t. So if you write, still write acceleration. Now velocity is equal to, we got x naught omega cos omega t. Now if you want acceleration, it is equal to dv by dt. Acceleration a is equal to dv by dt is equal to d by dt of what is v of t, x naught omega cos omega t. Now what is the differentiation of this? The differentiation of this is x naught is again a constant, omega into omega, omega square, cos omega t is minus sine omega t. That's what is written. Minus, I write minus, x naught is a constant, omega square sine omega t. That's what is written. So you can write acceleration is equal to minus omega square. What is this value of x naught sine omega t? X naught sine omega t is what? X naught sine omega t is x of t. So you can write in place of this, a of t is equal to omega square minus omega square. We have written it here first. Then what are the rest of the terms? X naught sine omega t. What is x naught sine omega t? It is x of t. So we have written x of t. So a peak is given by x naught omega square. It's a peak value. So this is a mathematical representation of vibrations or nature of vibrations, which we have uh, termed in terms of displacement, velocity, and acceleration. Now coming to piezo seismic transducers, they are for the measurement of acceleration, and we'll see what are the mathematical formulas and what are the types of accelerometers and potentiometric accelerometers, LVDT type accelerometers, piezoelectric accelerometers. Devices used for measurement of acceleration is an accelerometer. Thank you.